Hi everyone, today we are going to see the expression for thermal conductivity of a metal. It is given by the symbol K. The definition for thermal conductivity can be taken from this formula Q by dA dt by dx. The unit being watt per meter per Kelvin. The definition for coefficient of thermal conductivity is the quantity of heat energy flowing through the material per unit time across unit area of cross section per unit temperature gradient. Even the amount of heat energy can also be written as quantity of heat energy. Quantity of heat conducted or amount of heat conducted through the material or the metal per unit time across unit area of cross section, that is 1 second unit time. Unit area of cross section we can consider it as 1 meter square for simplicity. The temperature gradient is dt, denotes difference in temperature, and dx denotes the distance between the temperature taken at the two ends of the metal. For example, let us consider a metal rod as shown here. It has two ends A and B. Let the source of heat energy is kept at the end A, so it is called as the hot end. It is maintained at a temperature of T1. Here B is called as cold end, the receiver end. It is at a temperature T2. Let the distance between the two ends be 2L, or the length of the rod is taken as 2L. Let C be the center of the metal rod and C is also maintained at a distance of L from both the ends A and B, equal distance from A and B. Let us consider the area of cross section of the material be A or A1. So I am maintaining here also A1. I repeat the definition. Coefficient of thermal conductivity can be defined as the quantity of heat energy flowing through the metal per unit time across unit area of cross section per unit temperature gradient. The temperature gradient is here from the diagram. dt is T1 minus T2. If I am taking a thermometer and measuring the temperature at the hot end, let us take it is at 100 degrees Celsius, and I am measuring the temperature at the cold end. Let us take it is at 60 degrees Celsius. Let the length of the metal rod is 1 meter. Then temperature gradient is dt is T1 minus T2, 100 minus 60 degrees Celsius, I'll get 40 degrees Celsius. For simplicity, I am explaining this. dx is 1 meter. So dt by dx is the temperature difference with respect to distance. Even we can take it as thickness also if I am going to measure it between along the thickness wise. Now it is about the length. So the definition is over. The unit is watt per meter per Kelvin. the expression for thermal conductivity of the metal. From the diagram, it is clear that the electrons in the metal will have excess of heat energy at the hot end when compared with the electrons at the cold end. Since they are at higher temperature, these hot end electrons will possess excess amount of heat energy when compared with the electrons at the cold end. So hot end electrons have excess energy and the electrons are in requirement of energy at the cold end. We can call that as deficit energy also. Now we are going to derive expression for coefficient of thermal conductivity. Q divided by TA. From this particular formula, unit time. So T is taken as 1 second unity. Unit area of cross section, it is 1 meter square, and dt from the diagram, it is T1 minus T2, and dx here from the diagram, it is 2L. So I am rewriting this equation. Q divided by T and A becomes 1, and dt is T1 minus T2 divided by 2L. dx is 2L. That is Q divided by dt by dx. I have rewritten in this way. Or Q into the denominator of the denominator is the numerator now. Q into 2L divided by T1 minus T2, the temperature difference. So it is the coefficient of thermal conductivity of this metal, the base equation. Now the energy is taken by the electrons. Excess energy is taken by the electrons from hot end towards the cold end. In this way, crossing this C, middle area C with area of cross section A1. Throughout, it has equal or uniform area of cross section. So what is the amount of heat conducted by the rod from hot end towards cold end? That is Q, amount of heat conducted or quantity of heat conducted. Q is equal to, this equation can be rewritten as K T1 minus T2 divided by K is here, K into T1 minus T2 divided by 2L. Since Q, quantity of heat energy, it is taken with the unit joule. So we are going to find how much amount of heat energy is conducted by this metal rod from the hot end towards the cold end. Now we are going for the movement of the electrons. If it is electrical conductivity, the electrons will take up a motion called drifted motion, unidirectional motion. But here the electrons will take up the direction in any one among the 6 directions. That is, the electrons can be taking up in this metal rod not with a drifted motion, but it will take up any one direction. Let us take it is along the positive x direction, positive x axis. So what are the 6 directions here? That is positive x, negative x, positive y, negative y. Now positive z, negative z. So in this way, we have 6 directions, but the electrons, the thermal electrons, the thermally accelerated electrons will move in any one direction. We are taking it as it is moving along positive x-axis. Now, how many number of electrons are there? Let us take, there are n number of electrons, n number of electrons in the metal rod moving with the thermal velocity v in any one among the 6 directions, positive xyz and negative xyz. So, the number of electrons crossing per unit area per unit time through C is taken as 1 by 6 NV. Now, we are going to consider the kinetic theory of gases. The movement of the electrons in the metal rod is just like how the gas molecules move in a container. So, we are going with reference to kinetic theory of gases. The average kinetic energy of an electron from hot end A towards cold end. The average kinetic energy of the electrons from the hot end towards the cold end or from the hot end is taken as 3 by 2 kB T1. At end A, the temperature is T1. Kb is the Boltzmann constant. Similarly, at end B, the average kinetic energy of the electron is 3 by 2 kB. The temperature at B is T2. Now, the heat energy transferred from hot end A towards cold end through C is taken as the number of electrons with thermal velocity v moving along x-axis, positive x-axis, with the average kinetic energy possessed by the electrons moving from A to B along the x-axis. I repeat it. What is the heat energy transferred per unit time, per unit area of cross section from hot end towards cold end across C in the metal rod depends upon two parameters. One is the number of electrons taking part in the movement plus what is the average kinetic energy possessed by it. So at end A, 1 by 6 NV into 3 by 2 kB T1. So cancelling 3 and 6 with twice. I am rewriting this formula as 1 by, here I get 4 NV kB T1. So this is the excess energy taken by the free electrons from hot end towards cold end per unit time, per unit area of cross section through C. Similarly, at end B, the electrons are in the requirement of the energy. So, how many electrons will take up the same? For example, if 6 electrons are giving energy, the 6 electrons will receive energy from the end B. If 6 electrons have excess energy, they will give the excess energy to the 6 electrons from B. Therefore, this will also be 1 by 6 NV. The kinetic energy is, at B 3 by 2 kB T2. Therefore, I will write 3 by 2 kB T2. T2 is less than T1. So cancelling the same like terms, I'll get 1 by 4 NV KB T2. It is at end B. So we get two equations here. So what is the net heat energy transferred from A to B? From A, hot end, towards cold end B in the metal rod, what is the net heat energy transferred? So it is from, just like if it is temperature difference, what is the net temperature transfer here? 100 degrees Celsius, it is 60 degrees Celsius. So net is 100 minus 60. In that way, so here the net heat energy transferred, or the quantity of heat energy transferred, is equal to the heat energy transferred at end A to end B. So 1 by 4 NV KB T1 minus 1 by 4 NV KB T2. So taking 1 by 4 NV KB as common term, I'll get 1 by 4 NV KB T1 minus T2. So this is the equation for Q. Q is here. Now substituting, Q is equal to 1 by 4 NV KB T1 minus T2 in, let this be equation number 2, and the equation number 1 is taken as here Q2, that is K, because we are here to find the expression for thermal conductivity of a metal, the general expression. So what is the first equation? K is equal to Q 2L, the length of the metal rod, divided by T1 minus T2. We need to substitute Q here. Therefore, we get Q is replaced by 1 by 4 NV KB T1 minus T2 divided by T1 minus T2. This is Q. Okay, this is Q. And then 2L is here. So this 2 and 4 get twice here. T1 minus T2, T1 minus T2 get cancelled off. Therefore, K is equal to 1 by 2 NV KB L. So L is the length of the rod. This is A, this is B, and 2L is the length of the rod. L is the length of the rod from the center at both the ends. It is equidistant. The C, the center of the metal rod, is at equidistant from both the ends, A and B, hot end and the cold end. So L is the distance travelled by the free electrons to give energy. Therefore, we know in physics, length is equal to, or the distance is equal to, velocity into time. But here, collision time or the relaxation time will be the same when thermal electrons are concerned. Therefore, because velocity is equal to distance travelled by time taken, therefore distance is equal to velocity into time. So now we are going to replace this with L. 1 by 2 NV KB. L is replaced by V and tau. Here the time taken is called as either relaxation time or the collision time. So here, after consolidation, 1 by 2 N, here we have V, here V, therefore N V square KB tau. So the thermal conductivity of the metal depends on all these parameters: n, number of electrons; v, thermal velocity, the second power; and then Boltzmann constant and its time, either relaxation time or the collision time. So this is the classical expression for thermal conductivity of the metal.